Good morning and welcome to this spring knowledge transfer event. Thank you so much to everybody who is joining us today alongside the River Deep Mountain AI Consortium, who will be taking us through a journey through the Ofwat funded project, which looked to demonstrate how machine learning models and remote sensors can help to enhance and improve catchment monitoring and planning. The project team will showcase the steps taken to build a selection of the models alongside best practice tips for ways of working and adoption of the solution. To get us started, here's a short video introducing Spring Innovation and our role in supporting innovation and collaboration across the water sector.
In our industry, innovation is happening everywhere, every day. With so much going on, it's hard to keep track. The sector is tackling big, urgent challenges, like climate change, aging infrastructure, and more, but not always in a joined-up way. That's where we come in. Spring is the central innovation hub for the water sector. We gather insights from hundreds of projects across the UK and Ireland, showing who's doing what, what's working, and where the next big transformation could come from. We connect problem owners with solution providers globally, both inside and outside the water industry, to share knowledge, find partners, and accelerate ideas. This means less duplication and more efficient use of time and resources. Whether you're looking to learn from others' experiences, find collaborators, or share your own solutions, Spring makes it easy. Together, we're speeding up innovation, driving transformation, and shaping the future of our industry, both in the UK and Ireland. Spring, accelerating water sector transformation.
So to summarise, Spring is here to help you deliver against Ofwat's expectations for best practice knowledge sharing across the water sector. We support delivery of the Water Innovation Strategy 2050 objectives, and through our knowledge sharing, we support the transfer of learnings from an innovation project to the wider sector, hoping to create project legacy that helps innovators to identify and adopt the right solutions at a greater pace. So I think it was last year or the year before, we partnered with Ofwat, the economic regulator for England and Wales, to build out a view of what best practice knowledge sharing looks like. The 6 principles we created were to learn from what already exists before committing to innovation projects, to target innovation insights to the right audience to meet our objectives. The insights are regularly shared through multiple channels from day one of the project, that sector knowledge is open and centralised, and that insights from both innovation successes and failures are shared, and finally that people are empowered to receive and embed lessons from external sources. So back to today, I'll just share a little bit about the agenda for the session and introduce our speakers before I hand over to the team. Before I do, I just wanted to remind the audience that we'll be launching a poll during this event to gain your thoughts. And answering our poll is the most impactful way you can help us make sure that these events are providing that value to you, your organisation and the wider sector, and that these showcases are supporting faster paced adoption of solutions. We'll be launching the poll at the break, so please make sure to submit your answers when you see that, and we'll also launch it at the end for anyone who didn't get a chance to answer during the break. So I'll now begin today's session with the importance of knowledge sharing, followed by an RDMAI overview, a little bit about the open source models, and we are going to have a short Q&A after that section today for anybody who wants to ask more technical questions about the models themselves. We'll then have a quick break. We'll go into developing action plans, a little bit about lessons learned and adoption of the solution, and then we'll have another short Q&A with general questions, so do keep putting your queries in the chat throughout today's presentation. We'll first hear from Angela McCosker, Head of Innovation, George Jering, Partnerships and Programme Lead, Nikolai Tarp, Qualitative Researcher, Daniel Pierce, Consultant Scientist, Chris Dawson, Senior Physicist, Giles Exley, Senior Environmental Consultant, Marianne Belal, Project Manager, Gustavo Ostos Rios, Head of Futures. So without further ado, I'll hand over to you, Angela, to kick us off.
Good morning, everybody. It's great to have so many of you on this knowledge sharing session. And I'm truly delighted to that the team are going to be sharing the River Deep Mountain AI project with you all. So if anybody who has seen me speak before and knows that with regards to innovation, I am very fond of the P's. And I think that the P's are very, very applicable in terms of this project. So first of all, the purpose of this particular project. I think that when we kicked off the idea for this project, it was deeply embedded in true purpose of really wanting to create healthy rivers for our communities, and that purpose was probably one of the strongest thing that united the team and all of the different organizations that came together to really go after using digital technologies to be able to achieve better river status across this country. So there is very little of a more higher purpose than what we were trying to achieve here. And with that purpose came some really, really stretching goals that we had set for ourselves. So secondly, the second P is the people. And I think for me, this is one of the things that has stepped this project apart for me. It's we deal with a lot of innovation projects, but this is really a standout project for me, just because of the different team members that have come together to drive the actionable outputs that we've actually had from this project. The people have all come from quite diverse backgrounds, and indeed at the inception of the project, most of the people on the team were females, which we all know in this sector is not something that happens very often. So a very, very special project driven by incredibly talented people. The third one has been process, and as you see from the work that has been created by the team in such a short space of time, process has been really important to put the right guide rails in place so we could actually move along at pace and really deliver the outputs that we have today. And then lastly, in terms of my P, is passion. And this project would not have been possible to have got us to the place that we are today without the passion of all of the people that have been part of this. So I really, I'm going to be handing over to the team now to actually share all of the incredible insights that we have gathered along this journey. And I think that we have had some blind alleys, some things that maybe haven't gone to maybe as well as we would have liked. And we have actually freely shared all of those lessons learned as well, which, you'll all know in innovation that those learnings and that journey is every bit as good as the end goal. But I guess my plea and wish from this session today is that it will pique your interest and that you'll actually want to get involved, because the biggest tragedy will be if we don't take forward the models and the learnings that we have from this project, because they are highly actionable and something that could be embedded in any of the water companies across the country. So I really urge you to open your ears, your eyes, your hearts and everything, and have a look and see what the team have created. So without further ado, I'm going to hand over to George, who's going to take you through what we've learned. Thank you.
Thanks very much, Angela. Morning, everyone. Many thanks for joining the course. So my name's George Gehring. I'm the program lead for River Deep Mountain AI and based within Northumbrian Water. So the purpose of the next 10 minutes really is to give you a quick overview of the project itself, who's involved, the aims of it, and really the status we're at with regards to the project. It's still live. We are an 18-month project, very ambitious project, Ofwat Transform project. We started formally launched in August of last year following the Northumbrian Water Innovation Festival, and we kind of operationally complete December and then formally complete the project in March of next year. So it's a fast-paced, fast ambition, and as Angela said, the model outputs themselves are only one part of the story in terms of what we're trying to share. So I guess from my perspective, we really see this as a foundational project. What I mean by that is it's creating a foundation of learning as well as the models themselves that are freely available for others to learn from, and for which we hope multiple end users can can take the learning, the outputs, and have different real world applications they can explore from what we've done within catchment management and planning. And I guess unapologetically, we are catchment focused, not asset centric with regards to our application of technologies and use cases. So just quickly, why water? Why now? So we know, there's a lot in the press at the moment with regards to the state of our water environment. Really, there is a huge amount more to do. And I guess a point of difference within our kind of project is we're really trying to take a more holistic approach to look at some of those technologies that are available to us to see how they can expedite, enhance, improve our understanding of the data and evidence we already have to make better use of that to inform decision making and to inform interventions and actions to improve the health of our water bodies. So that is river, coastal and lake. And so we're really trying to look at that opportunity those technologies have. Just because we have got the technology doesn't mean we should necessarily use it. So we're very much focused on challenges where it makes sense to apply it, where there's a useful application, and where we can challenge business as usual to try and provide benefit above and beyond. So in terms of the project itself, so the aim is to develop and deliver proof of concepts demonstrating how those three technologies, artificial intelligence, machine learning, and remote sensing, can help enhance and improve catchment monitoring and planning. And there are 3 points of difference, I guess, I'm trying to emphasize with the project, or sort of USP. So the first thing is we are very much working with what we've already got. So how can we make best use of the existing data and information that's already out there? And I call it a sort of an 80-20 split. The models that we've developed are based upon 80% of what information or what data is already available and freely available, through open source. So we do have some of our own monitoring that we've deployed through Xylem and our partners and citizen science work through the Rivers Trust, but that is very much to focus on validation rather than training. So the focus very much is on what can we do with what is there already. The second part of it is scaling and scalability. We're trying to create up to 8 models addressing a number of different use cases aligned to 3 themes. And those models are generalist models. So rather than trying to just create one model, which is focused on one catchment with one use case, we are trying to purposely test the technologies and our ability to develop and train a range of models that are more generalist, that have a number of applications when applied at a local or catchment scale. And that's kind of point of difference really with what we're trying to do. And we're also looking then in terms of making sure that the learning as well as the models themselves are all freely available and open access, as Angela said. So key point of difference there is that everything we're doing, we're publishing as we go. The models and the coding, the documentation is being published on GitHub, and our first version models are live already. And that will continue to do so. And we'll be looking to publish our final models shortly at the back end of this month on a kind of model by model basis. So the learning, what's worked, what hasn't, where we've got to, where we had hoped to get to, where we think we can go beyond the project, that is all going to be shared publicly for anyone to be able to see. Obviously, that in its own right then determines what data we can and can't use. So a key component of this project is that we've been looking to build models based on data that is either freely or publicly available or available through open license. So purposely avoiding kind of vendor lock-in or avoiding expensive commercial licenses that would be required. Why? Well, the purpose of that is so we can share it, but also so that the coding and the models are replicable and they're available for others to be able to look at that code, try and recreate the models should they wish, change them according to your own needs, or apply them within your own local setting and within your own local catchment data, for example. So the project itself, it has a very ambitious timeline. There are 3 phases really that the project's divided into. The first phase was discovery and definition. So we came to the project with some broad thematic areas. The first phase of the project really then focused on engaging with catchment managers, engaging with ENGOs, with water companies, and other expert stakeholders and user groups to try and get a little bit more detail, try and better understand the challenges for which the technologies could be applicable, for which there is a sufficient depth and standard of data available to us, and actually where we are able to acquire that data under license to be able to train the models. So that first bit was very much discovery and definition, and we launched at Northumbrian Water's Innovation Festival. And that discovery and definition is iterative. It's continued throughout the project through our various governance groups and through our technical advisory group, which we've kind of been liaising with on a very regular basis. Part of that discovery and definition as well was also looking at the data mapping and collection, and I'll come on to that on a separate slide. That has then led into us going from a large number of broader themes to settle on 3 themes with a number of specific use cases in each theme, with a view to developing a number of models aligned to each of those themes. So that second phase, that develop and test, that started November of last year, and that saw us develop that first iteration of models, looking at those use cases and those challenges, so specifically aligned to certain water quality parameters, where we're looking at either trying to understand, estimate, or predict different water quality parameters, such that we can enhance and aid catchment understanding by being able to do so. The first version of models was then published last year, and we've been continuing to work on those, both in terms of looking at sensitivity testing. So actually, what's the minimum viable parameters the models can run on? Point of that is to understand where we are restricted with data. What is the kind of minimum data that these models will be able to perform under, and therefore hopefully try and aid a broader application of the models for other end users. It's also then been looking at our own data collection as well, so teeing that up ready for the validation phase. So this phase 2 really is very much the training data, developing the first models, going back to end users to see if they seem fit for purpose, then continuing to develop those models through to fine-tuning, validation, and then benchmarking. So the validation very much looking at, okay, we've developed a model, it has a certain level of accuracy that we're happy with, and our kind of minimum has been looking for 65% accuracy for each models. Obviously, accuracy is only one metric, it's only one part of how we're trying to measure success of the project. And then going through to where we are now to looking at validation on unseen data, and then benchmarking, so comparing with other existing tools or models out there to see how useful our models are and how they compare, how much broader value, where they do or don't provide value above and beyond what's currently available. So there's a range of data that's been utilized. So from a training perspective, we've worked very much with what is already available on the scale of data needed to produce generalist models. So there's a bias there towards water company data sets, where we've worked very closely with Stream to procure those data sets, to acquire those, and also then open license data sets such as Environment Agency data set, WIMS data, other data available through the Catchment Data Explorer, crop maps, and various Sentinel satellite data. The second part of it, as I mentioned, has then been the data acquisition, new data acquisition for testing. That's been led by Xylem, working very closely with the Rivers Trust also. And part of that has been to look at using citizen science data collection, in particular for phosphate, to support and augment our own continuous water quality monitoring we've undertaken for the project, and to help validate the models, as well as giving us real insights into the efficacy of citizen science data versus continuous water quality monitoring data. And so the 3 themes we settled on, so modelling high priority pollutants, designing an optimised monitoring plan, and getting more value from continuous monitoring. And those are chosen on the basis really of the ability to add value and have impact within catchment management, born out of need, stakeholder needs, scalability, and the potential of AI to provide benefits. So either cost savings, hopefully efficiencies, or just the ability to process large amounts of data over a short space of time beyond, human limitations. Each of those themes has a set of models underneath them, and we'll hear a bit more from some of our technical leads on those shortly. And so where we are now is we have developed 8 models. We're in the process of publishing final version of 6 of those, 7th shortly, and working still on our 8th model looking at open anomaly detection. So the things really take home for me is to really stress the importance of collaboration with this, the diversity of thought and challenge we've had. And as I said at the start, really we want this to be a foundation for others to learn on. And our intention, our hope is that the documentation, the models will provide value and others can see how you might be able to use them within your own setting, within your own business, and absolutely improve upon them, take them above and beyond where we've got to with Riverdeep. So thank you very much. I'm going to pass on now to Nikolai Tarp from Cognizant Ocean, who's going to take you through the first set of open source models.
Thank you, George. Yeah, in the next 40 minutes, me, Dan, and Chris will take you through each of these themes and the related models. But first, I just wanted to show you this QR code, which you can scan. And if you follow the link, you'll get to our GitHub, where all models and documentation will be uploaded and published. We've currently uploaded the early versions back in June, but in the coming weeks, we'll release the final iterations of our models and the documentation. So please bookmark the link or follow our GitHub page to be notified when we upload the latest versions. I'll just give you a few seconds to scan this if you want to. If not, I know that some of these links will also be shared in the chat as we go through the presentation. So yeah, hi everyone, my name is Nikolai. I'm part of Cognizant, and in Riverdeep Mountain AI, I've been the theme lead of theme 1. And as George just told you, as part of phase 1 of Riverdeep, we identified a range of themes where we see that the application of AI and ML have the potential of improving how we understand and manage catchments and water body health. As mentioned, I've been working on theme 1, which is focused on modeling high priority pollutants. And the overall objective of this theme has been to get more out of the data that's already being collected. We wanted to apply AI and ML to develop cost-effective and time-efficient ways of modeling high-priority pollutants and filling gaps in existing data sets. And as most of you are aware, a lot of money is already being spent yearly in efforts to fill existing data gaps by adding in additional monitoring. But often it's too expensive to make this monitoring permanent, and it also doesn't scale very well. And at the same time, these currently scarce data sets are used to make big and expensive investment decisions. And this is a big challenge. And in order to address it within this project, we've broken this challenge down to smaller building blocks or models that all aim to fill in current data gaps, both by filling out the blanks in the past and by predicting the future. And for this theme, we've focused on river flow, E. coli, and orthophosphate, with the overarching goal being to improve our ability to understand water body health, pollutants, sources, and impact. And as George also mentioned, all models in this theme has been trained on a national scale using data from across England, Wales, or Scotland, with the intent to create more general models that can be used in different areas by different stakeholders. And the first model is the open flow model. And we decided to focus on river flow as it plays a critical role in predicting floods, identifying pollution sources, tracing pollution, and managing abstraction. However, flow data is often limited due to the higher cost of monitoring, leaving many water bodies and rivers ungauged. And we wanted to explore how AI and ML can help and be used to fill in these gaps. So by collating available flow data with relevant weather and catchment attributes, we've trained an AI and ML model that estimates historical daily mean flow in gauged and ungauged rivers. And having an overview of historical data, historical daily mean flow can also be used to infer other key metrics, such as mean flow, Q95, and help create flow duration curves. And for the model training, we've mainly relied on two datasets, CamelsGB and Hydrology Data Explorer. With the CamelsGB dataset containing relevant attributes and weather data for all gauging stations across Great Britain, and the Hydrology Data Explorer providing quality controlled daily flow data from across England, with access to more than 40 years of data across more than 400 different catchments. The model itself that we've built is split into two layers, a long short-term memory model, or an LSTM, which is a type of recurring neural network, and then an encoder that handles the catchment attributes associated with each catchment. And the output of each of these layers are merged together through concatenation, which produce the estimation of daily mean flow in cubic meters per second. And briefly, how the LSTM model works is that it takes the past 30 days of weather data and use that to make an preliminary prediction of the daily mean flow, and then this prediction is calibrated using the catchment attributes. And this approach can be applied for several years back in time to estimate what the daily mean flow has been based on the weather and individual catchment attributes. And some considerations for replicating this model at your own end is that the OpenFlow model is a proof of concept, and it helps us show that it's feasible to use AI and ML to estimate flow in gauged and ungauged rivers. And in order to replicate and operationalize this model, it requires a continuous data pipeline, providing data that's similar to the CamelsGB setup in order to use this model on new catchments and rivers. The second model in theme 1 is the Open E. coli model, which actually includes several models, which I'll come to in a minute. Currently, monitoring E. coli is constrained by the time it takes to do a lab test and get the response back. The process is slow and expensive, and it does not provide the necessary information to bathers at the speed that they need it. Because knowing that a bathing water was contaminated by E. coli 2 days ago is not very helpful to swimmers or other people interacting with a water body. And we wanted to see if we can use AI and ML to provide a trustworthy estimation of E. coli contamination and improve people's ability to make an informed decision before entering the water. So by combining available E. coli lab samples from England, Scotland, and Wales with relevant water quality parameters, weather, and catchment attributes, we've trained models that predict the current risk of E. coli in bathing waters without a 2-day delay. And we've developed an advanced and a light version of these models. The two models vary in coverage and in the data that they need to run. And during our train tests, we've seen an 80% accuracy for the advanced model and 87% accuracy for the light model when classifying the E. coli contamination as either above or below a 500 CFU threshold. And for the model training, we've relied on several types of data. We've used water quality samples, primarily from the EA, weather data, satellite data, land cover data, and then a lot of E. coli samples from England, Wales, and Scotland. And using XGBoost, which is a machine learning library, we've developed 4 types of models. And these 4 types of models can be grouped into 2 overarching categories: the objective that they have, and then the data that they rely on. For the objective, we've developed an estimation and a classification model. The estimation model uses the input data to estimate the exact E. coli concentration in a bathing water, whereas the classification model classifies the risk of E. coli as either above or below a binary threshold. And for the data that the models rely on, we've developed an advanced model that use water quality data together with land cover, weather, and satellite to make its estimation, and a light model that only relies on satellite, weather, and land cover. And lastly is our open orthophosphate model, which is addressing the perhaps most difficult challenge that we've worked on in theme 1. Orthophosphate is a high priority pollutant for regulators and water companies, but monitoring is often only done using infrequent grab samples. But orthophosphate levels play a key role in the ecological health and regulatory classification of a water body, but it's expensive to monitor, especially continuously. And this gives an infrequent picture of one of the most defining pollutants in water body health and how it fluctuates over time, making it difficult to understand where it comes from in a catchment. And during our early stage interviews, we were told that a surrogate for phosphate would be a game changer for the industry. So we set out to see if we could use AI to fill the current gaps of orthophosphate data and find a way of estimating current levels using proxy parameters. By applying AI techniques to water quality data collected by the EA over the past 24 years, we've trained a model that estimates orthophosphate using up to 45 available water quality parameters. And as this challenge is very interesting for the broader sector, others have already tried to approach this with AI or ML, but with varying success. So to try something new, we decided to try a different and perhaps more complex approach to solving this. Using a hybrid approach, we've leveraged machine learning together with a chemical clustering approach and subject matter expertise to define a list of 45 determinants that the model rely on for estimating orthophosphate. And in most cases, all 45 determinants will not be available to make an estimation, but the model can be run with as little as 6 determinants and still make an estimation. But the performance, of course, is likely to increase with the number of determinants used. And these determinants, the 45 determinants, include ammonia, nitrate, pH, temperature, and more. And the most optimal way of using this model is by running it on existing EA water quality archive data to fill in orthophosphate data gaps using the determinants already sampled by the EA. But the model can also be run on newly collected data from SONS or citizen science. However, this will influence the performance. During our validation, we've tested the model in various types of catchments, including wet, dry, high base flow, low base flow, rural, and urban catchments. And in general, what we've seen is that the model performs better in situations where the orthophosphate is low, and its error increases in situations where the orthophosphate levels are high. So some considerations for replication. As mentioned, the model, the most optimal way of running the model is on existing EA water quality data, as the model depends on being supplied an existing EA sampling point. If not supplied, the model will still run and it will still produce an estimation, but it will do so without any location-specific knowledge, and the performance is likely to be affected. And that concludes the overview of theme 1. And now I'll hand it over to Dan, who will tell you about theme 2.
Perfect. Thanks very much, Nikolai. Good morning, everyone. My name is Dan Pearce. I'm a consultant scientist from WRC, and I've been leading theme 2 throughout the River Deep project. So as you can see from the screen, theme 2 really is focused around this idea of trying to optimize catchment monitoring and understanding by using remote sensing and AI machine learning techniques to help reduce the financial costs associated with designing and implementing water quality monitoring schemes. And really theme 2 can be split into two main building blocks. The first is based around the idea of using remote sensing and AI machine learning techniques to identify pollution sources that we don't typically have a lot of information about, or kind of pollution sources that are typically more challenging to pinpoint without kind of in-person expensive catchment walkovers, and therefore we're generating some cost savings and efficiencies that way. And then the second building block looks to create a high-level water quality risk mapping framework, which I'll touch on shortly. So the first model we created as part of Theme 2 was an AI machine learning object detection model to identify circular agricultural slurry tanks. Of course, slurry tanks aren't necessarily a source of pollution if they're operating correctly, but the idea behind this building block was to automatically map or locate slurry tanks so that further investigations could be undertaken by the users if there was a concern that slurry tanks may be contributing to water quality pollution within a catchment. And hopefully the model would therefore have save a significant amount of kind of manual desktop work or in-person walkovers. The AI machine learning model that we use is called YOLO version 8, and really the only data input it requires is relatively kind of high resolution aerial or satellite imagery. On the right, I'm hoping everyone can see a nice graphic that gives you an idea of how the model works. It's a black box for me, but I'm hoping that's just from my side. Essentially, when the model identifies a slurry tank, the model creates a boundary box around the tank and also gives a kind of confidence value from 0 to 1, which essentially is just showing how certain the model is with its detection. So 0.9 would mean the model is pretty certain or almost certain it's detected a slurry tank, whilst 0.5 would mean the model's not quite as sure. Final model performs really well. From our kind of final validation, we got a recall value of about 98%, which essentially just means the model almost never misses a slurry tank within an image or within a particular area. The precision value is slightly lower at about 70%, which means the model has a slight tendency to kind of misclassify similar circular structures as slurry tanks. So in other words, generate some false positives. However, we think this is the better way round and probably prefer to potentially producing high rates of false negatives and missing slurry tanks that way instead. The outputs from the model can also be really easily turned into a GIS shapefile format, and that layer then can be added to whatever maps or tools you are already using. So you'll notice then Theme 2 follows an agricultural theme, and the second model developed really focuses on identifying bare cropland at sub-annual timescales. So as I'm sure everyone here knows, there's plenty of land cover data sets that you can access already, and they often include a bare soil class. But generally speaking, these are generated on an annual basis and can often be quite costly to purchase depending on the resolution that you are after. So our model combines Sentinel-2 satellite imagery and remote sensing indices with some kind of geospatial processing to identify bare croplands at the field scale and then compare how those areas of bare cropland change over winter and summer seasons. So the idea being, hopefully, outputs from this model can help users understand where the risk of soil erosion and runoff increases, particularly during wetter periods of the year. We validated the bare croplands model across 19 catchments within Britain. Again, the model performed really well with overall accuracy score of around 94%, and performance remained relatively balanced across different soil types as well, which was great to see. Current limitations with the model mainly relate to kind of sensitivity to soil moisture and snow cover, as well as just simply having enough kind of cloud-free imagery, particularly during the winter months. Okay, so moving on to the third model in Theme 2 then, which aims to identify poached land at the subfield scale. So we're zooming in even further than the bare croplands model and looking within those field parcels of land instead. And so for the purposes of this model, the term poaching is kind of used as an all-encompassing word to describe disturbed ground that could be caused by a trampling of livestock, but also other activities such as kind of rutting from farm vehicles and things like that, but ultimately resulting in things like soil compaction, vegetation loss, and again, that increased risk of erosion and runoff. This model begins by enhancing 10-meter resolution Sentinel-2 satellite imagery up to a 1-meter resolution using an existing AI model called Sentinel-2 Deep Resolution 3. A number of kind of mask layers, if you like, are then used to filter the results down by removing certain land cover types and things like that, until we're left with what we hope is poached land. On the right of the screen, you can see an example of the model results, which are shown by the kind of red layer. And that image is just flicking between the upscaled 10-meter resolution Sentinel-2 imagery, which the model runs on, and then high resolution imagery that we use to validate the performance of the model. Overall, the poached fields model achieved a kind of moderate performance, I guess, with an accuracy of around 65%. It doesn't necessarily sound brilliant when you kind of initially say it out loud. However, when you consider that effectively the model is using 10-meter resolution satellite imagery to identify really quite small and granular ground disturbance, I think it's actually pretty impressive, and I think it does represent a really exciting and quite unique model output that hasn't really existed before. It's probably also worth mentioning that we didn't test the model performance using kind of high resolution imagery as the input data, but we think that definitely could hold a lot of potential for future work. But as high resolution imagery is generally not free or open source, it's not something that we've touched on during this project. Okay, so that wraps up the 3 models that make up the first building block in theme 2, and brings us on to the second building block and the final model in theme 2, which aims to build up a water quality risk map of a catchment using open source datasets and some kind of high-level assumptions. And you can see an example of what this risk map looks like in the video on the right of the screen. The risk map is constructed using individual risk layers, and each of these risk layers kind of represent a particular source of pollution. In our final iteration of the model for this project, we've included risk layers for CSOs, so combined sewer overflows, wastewater treatment work, final effluents, agricultural diffuse pollution, both from livestock and arable, urban runoff and highway runoff. The model also includes some kind of basic dilution calculations and risk transportation mechanisms, I guess, as pollutants travel downstream through the catchment. And within this project, we've created risk maps for ammonia and for phosphate, but there's absolutely nothing stopping people picking this model up and adding in other pollutant layers if you so wanted to do. I think one of the main challenges as we developed this model was not falling into the trap of creating another piece of deterministic water quality modeling software, as plenty of those already exist, but instead this map really functions as more of a kind of semi-static annual average risk for a catchment, rather than focusing on specific event-based timescales. So in other words, we're not trying to understand water quality risk during a particular rainfall event. Instead, we're looking at kind of bigger picture, in general, where is my water quality risk highest within a catchment, and therefore where should I focus my attention on for future investment. And at the same time, we're also interested in what is generally contributing to my water quality risk in terms of source apportionment. Is all my water quality risk coming from my combined sewer overflows, or actually are there multiple different sources contributing to the issues in my catchment? Overall, I think it's a really exciting model. It's very easy to run. It's almost click and go, and all the data ingestion and processing is automatic. We tried to design the model framework in a way as well where people could relatively easily add additional risk layers in or kind of improve different aspects of the model if they wanted to. So for example, the flow and dilution estimations are relatively high level at the moment, but a more complex flow model or flow data could be used to improve these if you so wanted to do that. Or assumptions about pollutant loads could be improved if the user had more relevant data that they wanted to include. So for example, currently for wastewater treatment final effluents, we estimate risk primarily using kind of discharge permit data and some other assumptions. But if you for example, were a water company and you had actual final effluent sampling data, you could potentially edit the model and try and use that instead, and so on and so forth. Hopefully that kind of makes sense. This model is a bit more challenging to try and validate how well it performed, but so far we've tried what we did was try comparing the model output to existing EA sampling data, and we're currently in the process of kind of benchmarking the model outputs against SAGES results, existing SAGES results, and WFD RNAG, so reasons for not achieving good. That is everything from me for theme 2. So I'm going to pass. Yeah.
Dan, sorry, just before you hand over, the animation on the slurry tank slide wasn't working while you were speaking. Would you be able to just rerun that slide and get it?
I can try. It was working when I tested.
If not, we can fix it in edit.
Yeah. Sorry, everyone. Sorry about that.
Oh, yeah, no problem. We'll fix it in edit. Don't worry.
Cool. I'll hand over to Chris then from Xylem.
Good morning, all. So this is talking about theme 3 now. So theme 3 is just a single model versus the theme 1 and theme 2 had a couple of models per theme. And it's focused on doing event detection or anomaly detection in continuous water quality monitoring data. That's a major need that we found emerging when we did our stakeholder engagement early on in the project. The Section 82 is a huge project that's just on the horizon. It's being implemented at the moment by all the water companies in England. It's about 25,000 monitors that are having to go in across England, upstream and downstream of wastewater treatment works, final effluent and combined sewer overflows. And when we were talking to the stakeholders around the water sector at the beginning of the project, one of the real urgent needs that came out of those discussions was the need to do better analysis on the data that's going to be produced by those monitors, and really trying to create as much value as we can from the kind of the regulatory requirement of putting the monitors in. What extra benefits can we get from that, and what can we do for customers in terms of providing a bit of more information around the data as it comes in. So yeah, the 25,000, the monitors going in, they're monitoring pH, dissolved oxygen, ammonia, conductivity, turbidity, and temperature. They have to measure every 15 minutes if there's an event going on, and 1 hour when there's not an event going on. But crucially, they have to make that data publicly available within 1 hour of it being recorded. So any analysis that has to go on, if you want to get that analysis done before the data is made public, it's got to be done within that 1 hour window, which becomes very challenging with the number of monitors and having to have a human do that processing. It's clearly somewhere there's an opportunity for using AI and ML to do some processing and add some extra information, add some value to that data. So in terms of why we think we need the model, like I say, it's a case of processing the sheer quantity of data that's coming in. You're talking in the billions of data points every year. Each water company's got to look at their hundreds to thousands of monitors that they're going to have out in the country. And we really want to try and wrap a narrative around what the data is saying, rather than just producing the raw data of those different parameters that I mentioned. That's not always the easiest thing to interpret for the public, certainly. Even for water sector experts, it can be a challenge to try and understand the exact story that's going on. So we wanted to build an algorithm to interpret that data, try and understand what's going on, certainly be able to detect when there's an event that's of interest happening versus when there's sort of kind of quote normal situation happening in the river. The difficulty as well is that what normal looks like varies massively across the country. Different geography, different geology, different biochemistry in the river has a massive effect on what that data looks like. So what's normal in one river might not be normal in another, and therefore if you're looking at using kind of static thresholds, that can break down if you want to transfer that methodology from one catchment to another. The other aspect is that, let's say you had an event at 2 in the morning, for example, on a particular monitor. It's highly unlikely that someone sat in a control room staring at all the live streams of it coming from each monitor. So it's a really good example of somewhere that if we can put a model in that processing chain of when the data comes in that does some analysis, it can deliver that analysis in a timely fashion so that when someone, a member of the public, is looking on a public dashboard, for example, they might be able to get that narrative alongside the events they're seeing. So, for example, if there was a heavy rainstorm, but it was just a rainstorm that they were seeing on the event data, the model might be able to look at that and say, okay, there is clearly a peak or a trough going on in this data, but actually, based on the analysis, this isn't something to worry about. The other side might be that if there was a real spill event, for example, or an agricultural diffuse pollution event going on, we might be able to, in the future, wrap a narrative around that and say give a bit of an explanation of what's happening. So in terms of what we wanted to achieve, what we really want to do, we want to do automatic, safe processing of water quality data. We're looking to identify the events in that raw data and in this project, group them into events that look the same to make that human-powered analysis a bit easier when they come to look at the data and review what's been going on. So for the moment, we're finding the events among the time series themselves and not putting labels on them specifically at this point. That's one of the things that we think is on the cards for a future project, for future work, is to be able to start labeling what each event is. For the moment, we wanted to build a really solid foundation of a sort of data ingestion pipeline that requires very little in terms of inputs. It's just the water quality data that's required. Does the analysis and says, okay, there's an event going on in this section of data. So for a water company expert that's looking to deploy these monitors, they could focus on just that section of the data to try and understand what's been going on, and they could sort of not have to give so much attention to the normal data. So yeah, the human operator at the moment is still in the loop, and absolutely, I think for the moment that's really important. That one of the things we need to do in the future is sort of train in that knowledge of when this parameter increases and this parameter decreases, that means a certain type of event is happening. We're trying to create really a springboard into the next set of projects where water companies are putting this kind of model into their pipelines. Want to give them the solid data processing foundation. There's an enormous amount of cleanup that we do in this project, in this model, and we wanted to make it kind of uniform across the different monitors. So in terms of what we actually built, yes, we've got a model built. It requires only the water quality data, so there's no weather data or extra land cover or contextual information required. Like I said earlier, crucially, that means it has to be capable of not just using static thresholds. It has to sort of learn what normal looks like for any given monitor in a particular catchment. So yeah, what we've built here tries to learn what normal looks like. It does a whole load of cleanup on the input data, looking for gaps, looking for continuous sections of data, cleaning those up where it can. We extract the patterns that we'd expect to see in this data, things like where we've got daily cycles in the data, yearly cycles in temperature. You can imagine every day there's a cycle in temperature, and every year there's also a cycle in temperature. Removing those behaviors that we'd expect to see, and then we operate on what's left when we've removed those. So we're clustering that data into different events that have got similar kind of fingerprints according to all the different parameters at once. And then we're picking out which of the data there looks unusual. And then the clustering itself is happening on just the unusual data rather than this version of normal. We don't try and include those in events. That's sort of the baseline behavior. And then the interesting events happen outside of that. So in terms of what you within your organization would need to do to use this, very little with this model, actually. It's almost, we are about to release in the next couple of months this model up onto the GitHub repo. You will only need sort of CSV files of the individual water quality parameters. It can be for sort of, really you're going to want about 6 months to a year plus worth of data to be for the system to be able to learn properly what a yearly cycle looks like. You will be able to use it on less than that, but in terms of kind of trust in the output it's producing, we're recommending sort of 6 months to a year worth of data as a minimum, and then beyond that, as we get further into AMP8 and into AMP9, as these monitors are deployed, the longer they're in, the more expertise they're going to have over a particular site, what normal looks like, and therefore the better they're going to be able to distinguish these events. Yeah, so like I say, if you've got monitors deployed, do get in touch with us. Come and speak to us about using the model. We can definitely try and help you get set up with it. With that is me done. I'm going to hand back to Leah, I think, here. And I think we're going to do a bit of a question and answer session.
Thank you, Chris, and thanks to all the presenters so far. As you can see, there's a QR code on the screen that will stay up throughout the technical Q&A. So if you are interested in learning more outside of what we can fit into this small session, do scan that and let the team know which model you are most interested in for a technical exchange. Great, so to get us started, we've had a few questions in already. So one from Tom is, I think it got answered in the chat, but just so everybody gets a chance to hear, why is it that phosphate is a game changer? And I think that's for Nikolai.
Yeah, thank you, Leah. Thank you, Tom. So Stefan already answered this in the chat as well, but I guess it's not phosphate that's a game changer. It's a surrogate for phosphate that's a game changer. That's what we've heard in phase 1 during our interviews and stakeholder engagement. Mainly, as Stefan also writes, is that a common way to measure autophosphate is with reagents, which means that auto-sampling this is expensive and requires more maintenance compared to ammonia and other nutrients. So if there's a more I guess cost-effective way of sampling this, it would be very beneficial. And that's what we went on. Hope that answers the question.
Perfect, thank you. Nikolai and Dan, sorry, would you be able to just pop your cameras on for this portion? Thank you. Cool. And then a question from Andrew on the E. coli model specifically. How does this model compare to existing conventional models, e.g. the EA pollution risk forecasting? Also, E. coli levels at 500 CFU over 100 mil is high to identify risk. I think PRF cutoff is about 60 over 100. What predictive variables are used?
Yeah, I'll take that one as well. The first part of the question, I also put this in the chat, but we've been in contact with the EA PRF team to understand how the two approaches kind of complement each other. And we're also working on a benchmarking exercise at the moment where we'll try to compare the different existing tools. So this information, I'm not sure at the moment exactly how they compare, but we're working on benchmarking them. Second part of the question, we've decided to use 500 CFU as a threshold based on the EA coastal bathing water regulations, where below or equal to 500 is the threshold for good, whereas for inland bathing waters, the threshold is equal or below 1,000. And throughout the process, we've experimented with both thresholds. So when you look at the documentation that we'll be sharing with the report, you'll also be able to see how the model performs given the different thresholds. And then I think the last part of the question on I guess the parameters used for the predictions, the advanced model use water quality parameters such as water temperature, suspended solids, ammonia, nitrate, phosphate to make the estimations. And we are aware that some of these are quite tricky parameters to obtain. That's why we also created a light version of this model that only relies on weather, land cover, and satellite data, which is much easier to obtain.
Great, thank you. And how does the open flow model account for anthropogenic influences on river flows, especially discharges and abstractions?
Yeah, I'll answer this one as well. So the CAMELS-DB dataset that we've been using has an information on human influences such as weirs and dams and abstraction. However, the model currently just takes this as a static input that a catchment has these human influences. It doesn't take into account any of the dynamic data related to that, such as how much is being abstracted and when it's being abstracted.
Perfect.
And then there's, I guess Andrew has a follow-up question. If the models be used to predict river flows with and without the effect of obstructing discharges? I would say so. That's an input that you can remove from the input data that you feed into the model, giving it the knowledge about human influence in the catchment and not giving it that. Hope that answers the question. I'll put that in the chat as well.
Thanks, Nikolai. On the continuous monitoring model, is this run on raw data, or has the input data been pre-cleaned to remove data affected by instrument fouling, calibration, drift, etc.?
Yeah, so I've put a reply in the chat as well, but yeah, so the short answer is it's done on raw data. A big chunk of the model that we're producing at the moment is doing exactly that, is the cleanup process that's required. There's a huge amount of work been done on finding gaps, looking at removing trends, keeping things nice and flat and level to be able to do the event detection, and things like sensor fouling and drift and those kind of events, that we include those in the sorts of events that we're detecting, right? So from the sensor's point of view or from the algorithm's point of view, those kind of things occur and look unusual to the system, so it regards them as an unusual event, detects them, and they would get their own sort of label in the output results.
Great, thank you, Chris. And how many different AI/ML techniques are you trying per problem before settling on the presented solution?
Lots. Is that a good enough answer? It varies massively across all the different building blocks here. It's I would guess in 5 different sort of major categories of techniques, roughly, as if I had to pick a number. It's massively affected by which type of problem you're trying to solve. If you're trying to do flow, for example, that's time series estimation. So there is a whole sort of catalogue of time series estimation techniques that are out there that you sensibly go and try, and that's the sort of thing that the team at Cognizant have done, going out and looking at the state of the art and sort of implementing them for the specific challenge that we're looking at solving here. Half of the challenge as well with any of these is really trying to understand what the problem is rather than what the solution necessarily is. Boiling it down to exactly what problem are you trying to solve, then you can start to understand, okay, based on the literature and sort of the expertise of the team, what methods do we think are most appropriate for that? But yeah, distilling the question down into exactly what data science problem are we trying to solve based on what the sort of ecological water sector challenge is, that to be honest I would say is the hard bit.
Perfect, thank you. And can the open flow model be used for discharge forecasting for input to another forecasting model, e.g. a lake model?
I would say right now the open flow model works primarily to estimate historical flow data. So it can be applied to predict tomorrow, but it's not set up for forecasting at the moment. It's mainly to produce key flow metrics for an ungauged catchment. So trying to really estimate that historical flow data.
Great, thank you. And how do you combine the different data sources like satellite imagery, sensor data, into a single model? And what technical challenges have you faced in making that data reliable?
Is that one for me, possibly?
I think that's one for anyone who has a thought to share on that.
It depends on the model, I suppose. So for theme 2, obviously the first 3 sets of models are more focused on using things like satellite imagery. Technical challenges in terms of making that data reliable. For example, the Bear Croplands model has struggled, particularly during winter periods, purely because there aren't enough cloud-free images during those times, and things like soil moisture and snow cover can affect the indices that are used from those. Chris, do you want to jump in?
Yeah, my comment on this was going to be, excuse me, I suspect the future of this kind of work in the water sector and probably a lot of different sectors is not, don't imagine one giant monolithic model that's going to solve all the problems in the water sector. I suspect the future is going to be a probably quite vast array of different models that are suitable for different tasks that talk to one another. You combine satellite data and flow or permit data by having one model look at the satellite imagery that's doing kind of finding the slurry tanks, finding the sources of risk, and outputting some data from that model, passing that data to a different model, which is then doing the risk mapping, for example. Right. So I think you don't try and not every problem is a nail if you've got a hammer type thing. If that you've got to try and choose the right tool for the specific section of the task that you're looking at. And it's totally okay to use a hybrid approach and sort of combine different models or agents or whatever you want to call them. That's what we do as humans in a team, right? We don't have one person that's trying to do everything, and we choose the best tool for the job.
Great. Thanks, Chris. Some great insights there. And have you used or are you planning to use the Earthwatch, Freshwater Watch nitrate and phosphate data at all?
Maybe I can jump in on this on a sort of citizen science point of view. Yeah, I saw the message. It's a really good call. So yeah, I was aware of that as a resource. It's one where we're trying to gradually open up the scope to sort of include more and more of these sources that are out in the world of all the different great citizen science data that exists. One of the projects we're looking at in the future is around sort of bringing together the different varieties of data that exist. So where we've got regulated data, water company data, and citizen science data, we're really trying to bring all of those together to get the best advantage out of all of the above. So projects like Earthwatch and the various local river trusts that are around, the sort of national level Rivers Trust, all the sort of wildlife trust action groups. There's a huge number of different communities around the whole country and the whole world that are doing sampling to get this kind of data. And absolutely, that is one of the activities we're looking at doing, is sort of trying to create a bit of a catalogue of who's got what, where it sits, how we can ingest it, and really building a community between the organisations to say, okay, we're trying to build this tool. We think it's going to help you with this task and this task. What do you have? How can we help? What do you need? And George, do you want to come in?
Yeah, thanks for that. I think it's great question. Just to build on what you said, Chris. So Laura, for that one, it's definitely the future of where we want to go. I think within the kind of confines of this project, we're aware we've scratched the surface of the application of citizen science data within the models, and it's probably been more of a bias looking at it for validation rather than model development and model training. That's because of, I guess, some of the constraints working with the amount, the depth of data we're using, the ability to look at proxies alongside specific parameters. Going forward, I think there is absolutely an opportunity for it. And Chris, Dan, Nikolai, and I, with others, have been kind of chatting a lot to Stream, looking at the outputs from Casco. I guess one thing we're purposely trying to avoid is where maybe the ambition for Casco is to work on the data standards and democratize the access to citizen science data. We're trying to democratize the development of tools that utilize said data. So we see what we've been doing and ourselves as a kind of recipient for that data, to then be able to put it alongside, whether it's regulatory or water company data. I think key part of that first step is actually the visualization of it and geospatially kind of referencing that data against other data. We've had a kind of play around with how we could take that further, but really interested to kind of go from the proof of concept models to then develop more operationally based tools that can make more direct use of citizen science data in terms of their application for it, for things like investment, scenario planning, elements like that.
Great.
But I think there will be some broader knowledge, some wider benefits we can point to in the write-up from this project, even just looking at the efficacy of where we have used citizen science data against EA continuous water quality monitoring, and our models, just to look at the comparison of how they're being used. And obviously a key part is what we're using the data for. What decision is being made on the basis of that data, and making sure that the data is fit for purpose for the decision and the risk associated with what it's being used for. Yeah, definitely an area we're looking to delve more into as a result of the outputs from River Deep.
Great, thank you, George. We have had one more question on the technical side of things, but just in the interest of not having to rush the presenters to give their answers, because we are at the time we should be going to break, I'll add that to the general Q&A at the end of the session, so you've got a little bit more time to answer it. So that brings us to the break. So we will have 10 minutes to go do what you want. You have your camera and mics off already if you're an audience member, so there's no need to leave the call or anything. You can stay where you are. And on the screen here, you can see another showcase that's coming up soon. So if you have any interest in sewer maintenance with Pipe Bot Patrol, also from Northumbrian Water, give that a quick scan for more information. We will also You'll notice we also included the link to our feedback poll, so please do make sure again to give us your insights on how you think the showcase is going so far if you do need to jump off, and we will put that link in the chat again at the end of the session so you can answer it before you leave too. Thanks everyone. Great, so welcome back from the break everybody. We are going to restart the session now, and we'll be jumping into hearing about developing action plans from Giles Exley.
Hi there, everyone. Good morning. I'm Giles Exley, a Senior Environmental Consultant at WRC, and I'll be talking about the work package that I'm leading, which is about developing action plans and enabling action. So work is ongoing at the moment to produce 4 use cases to demonstrate the potential model applications. Each of the use cases will provide an action plan for how stakeholders could deploy the River Deep models, along with an accompanying funding sources handbook, which with the aim of that being that stakeholders could review that and identify potential funding that they could apply for to then enable them to take action to improve water body health. So the use cases will each consider the current method for addressing the specific challenge or the specific operational need. So for example, this could be water quality monitoring, and then the use case will present a series of steps that the stakeholder would need to take to deploy the model, including things like the data requirements and if there's any considerations for how the model can be used. And then finally, the use cases will also cover how the models may help improve efficiency in a business's operations, whether that be through to time saving or financial efficiencies. So we've had some really excellent suggestions from the various workshops, innovation festivals and working groups for potential use cases that we could feature. So to help narrow down a list from over 70 potential use cases, we've developed a set of criteria that you can see on the screen now, which have been used to help us focus in on prioritizing the use cases to take forward and write up as part of the project. So the main focuses for these are on the feasibility and adoptability of the models. So can the River Deep models that have been developed actually address the use case challenges? And then we're also looking at the benefits and the impact of the use cases. So is there a tangible link to action? Things like whether there's regulatory relevance and links to ODIs. So is there a benefit for the customer or a benefit for the environment? And that's all being considered. So each of the use cases was given a score against the criteria, and it underwent screening. So each of the project partners have reviewed each use case with the scoring, and then the 4 use cases with the highest scores was selected, and these represent all of the 8 models that have been developed. So we also plan to publish this library of potential use cases and applications alongside the use case report. So all of that input from the various stakeholders and project partners will be shared of the huge array of potential applications that people see the models having. So we'll now look at each of the 4 use cases. So use case 1 focuses on how the River Deep models could help prioritize when and where water quality monitors should be installed and how many are required. So based on the Cunliffe report, We see this use case as demonstrating how systems planners could use the models as a tool for planning monitoring. So Cunliffe acknowledged in their report that there's a move towards a risk-based approach as well for deciding on monitoring locations. So as you've seen, the Open Risk Map model uses a risk-based approach, and we feel that this could be particularly helpful in identifying where those monitoring locations could be. We also feel that use case 1 presents a particular opportunity to highlight how monitoring could be improved beyond that which is mandated under Section 82 of the Environment Act, and also could be used by stakeholders to better plan resources, them and the location of their monitoring, but also and lead to cost benefit as well. So use case 1 we'll use the Open Risk Map, the Open Flow model, and the Open Anomaly Detection models. And the use case will focus on action plans that will demonstrate how the models can maximize value from continuous water quality monitoring. Also guide volunteering and citizen science efforts, help to evaluate the success of catchment interventions, support instant response by improving understanding of pollution pathways, all while being able to flag anomalies in continuous water quality monitoring data. So moving on to use case 2, this one's got a slightly different focus, which is on how the models could help support integrated catchment planning to enable effective evidence sharing. So in the Cunliffe report, it was acknowledged that there's been great success with the catchment-based approach, but the report highlighted that there's often more support required for decision making. So as we shift towards managing water systems with systems planners, there'll be a greater requirement for integrated thinking and catchment-based intelligence, and the River Deep models can help contribute to this catchment-wide intelligence approach. So this use case will help to demonstrate how the River Deep models provide a framework for bringing together data, helping stakeholders to understand the different challenges that a catchment is facing and to support them in planning and making decisions. This use case as well will also help to outline some of the potential next steps after River Deep concludes. As George mentioned in his opening presentation, a lot of this work is we see as being the foundation for more to come in the future, and to build on what the project has developed so far. So use case 2 will make use of the Open Risk Map, Open Flow, the Open Orthophosphate, and the Open E. coli models. And it will focus on action plans that will enable stakeholders to use the models for things like scenario planning for investigations, how the models could be used for AMP planning, how the models could contribute to drainage and wastewater management plans, and also for how resource can be targeted to where it is needed most in a catchment-based approach. So moving on to use case 3 now, this is a much more specific use case and focuses on how the E. coli classifier model could be used to automatically trigger real-time beach signage, providing timely public health alerts. So in the Cunliffe report, there was a call for a shift to include public health as a key objective in water management, and acknowledge that there needs to be improved ways of monitoring and improved warning systems. So the report highlighted, as you've already heard when the models were being presented, how there's often a lag in things like E. coli monitoring data where it needs to be sent, where samples need to be sent off to the lab, and it can take a couple of days before results are returned. So the Cunliffe report called for that there needs to be a better way of filling gaps between when the sample's taken and when the results are available, and it called for the use of AI and digitization. So this use case will demonstrate a proof of concept for improving public access to real-time information. So very simple for this particular use case, it will just be the Open E. coli classifier model. And then the use case will share an action plan for how a stakeholder could implement a very practical measure in the form of real-time signage to communicate E. coli risk to the public. And then finally, use case 4. So this use case details how the models could be used to identify water quality risk spots in a catchment in areas with intensive agricultural zones. So Cunliffe highlighted how agriculture has the most significant impact on the water environment. And as there's a move towards system planners, they will be responsible for setting the mechanisms to mitigate the impact of key sectors, including agriculture. There's already legislation in place that is targeting a reduction in agricultural diffuse pollution. So this is a challenge that there are real goals in place, and we see that the River Deep models could play a role in addressing this challenge of identifying where the water quality risk spots are, so that action can be taken. So this use case will use the Open Risk Map, the Open Poached Fields model, the Open Slurry Tank Detection, and the Open Bare Cropland models. So action plans for this particular use case include how the models could be used for things like drinking water safety planning, how they could be used to plan catchment scale interventions, supporting funding applications for enhancement in catchments, and also for improving the efficiency of things like walkover surveys, where the models can be used to identify risks in a catchment at a desk before sending people out onto the ground. So that was a brief overview of the 4 use cases and the work so far on developing them. Please do add any questions or suggestions into the chat. I will hand over now to Mariam and Gustavo from Cognizant to discuss lessons learned and adoption.
Thank you, Giles. Hi, everyone. The models and applications you have just seen are a testament to the commitment of the team. But successful innovation isn't just about the output. It's about the process and the learning and the adoption. My name is Mayim Bilal, and today Gustavo and myself would share the key lessons we learned throughout this ambitious project. We looked at what worked well and where we faced challenges. Learning from this program is crucial to inform not just our team, but the wider sector, and ultimately to strengthen the delivery of all the future innovation projects and ensure we continue to improve. So how we collected these lessons? We collected these lessons after extensive participant surveys and one-to-one interviews with project members and stakeholders. We grounded and grouped our findings into 3 essential themes. Let's start with the first one, that's partnerships and collaboration. The project created valuable partnerships, fostering open working and ultimately delivering tools which will have a long-term value for the industry. One key insight we heard repeatedly was the value of personal connection. Meetings in person early on was essential to build trust, improve communication, and keep the work on track. While the collaboration was strong, we learned 3 critical lessons about governance. The first one being the project began without a signed collaboration agreement, which created discomfort and uncertainty for partners. The lesson here is to get the main clauses agreed with the costed partners upfront. This provides clarity and trust among all partners from the very beginning. The second lesson is structural efficiency. we found that relying on early large governance and advisory groups slowed our momentum and decision-making. And we found that while these were essential for higher level guidance, smaller experts group were far more effective at solving issues, especially when they were empowered to make decisions. And finally, communication. We cannot assume that everyone shares the same language and understanding. It is absolutely critical for technical experts and subject matter experts to work together continuously to bridge that knowledge gap, ensuring the technical solution solves the real-world problem. The overall takeaway for this theme is that successful innovation relies on high trust relationships established early, but it must be supported by a lean, empowered governance structure. Our second theme addresses one of the biggest challenges in any AI project, data. We learned a major lesson that challenged a common assumption. Open datasets aren't always truly open. They may not allow reuse, transformation, or open source distribution in our case. Our early assumption that they were freely available and reusable led to delays in publishing our first iteration of the models this summer. The key takeaway is to get advice early, speak with an IP specialist about publishing rights and model distribution before working with any external dataset, and use existing resources. Tap into resources like the Open Data Institute, guidelines, and Stream to review data licenses and get clarity on data rights from the outset. Another critical insight is to invest time in data discovery. Don't just grab the first data set that's readily available. Exploring the right sources upfront will save you time later and ensure your models are built on the best possible foundation. Data isn't just an input, it's the foundation. Getting it right from the start will set your project up for success. Our final theme focuses on project delivery, where we learn the importance of balancing structure with flexibility. The key lesson here is that a clearly defined scope is essential, but flexibility is just as critical. Ambitious timelines left little room for review and reflection. More flexibility would have enabled deeper collaboration and stronger outputs. We also found that having a written scope for each work item helped prevent scope creep to a certain extent and encouraged ownership. Here, we also want to mention that don't underestimate the value of project management. It's what keeps timescales and objectives on track. And finally, standardize templates for documentation, code, and reporting early in the project. Every organization and every person has its own way of working, so agreeing on these upfront is essential. Doing this early with streamlined reviews improves consistency and ensures smooth delivery. The key takeaway for this theme is clear scope and alignment are necessary, but when developing something new, you must allow for flexibility. And remember, success doesn't end at delivery, it depends on adoption. So now let's look at how we approach adoption in River Deep Mountain AI. I'll give it to Gustavo to take it from here.
Thank you, Mariam. Yes, hi everyone. My name is Gustavo Ostos Rios, product designer and the features team at Cognizant. I'll speak a bit about adoption, right? So we are in the last few months of the program. The models are open, released on GitHub, but it cannot stop there. Organizations, people need to adopt these models to be truly successful, right? So it needs to become business as usual in that way by being adopted by the industry. So, but how do we ensure that, right? That's the hard work that needs to happen after this program ends, and therefore it's beyond of what we can cover, right? However, we are doing some activities to ensure that we get people to build awareness and move them already towards adoption. And this could be part of that, right? If you look at the graph, some of you might recognize in some of these steps, by starting to learn about the models, getting aware of what is it, how can I use them. Others might be already using similar tools or models, and some of you may also already be an expert, right? So our approach and activities in this sense are focused on getting early adopters of the model by passing on the knowledge, training people on how to use them, right? How to generate the insights for other people that will consume that information, right? And then there is the hard work that needs to happen into how you adapt these models into your organizations in terms of business processes, technology frameworks, which, well, that's a big challenge altogether, right? Some of the activities that we have done for this, for example, is well, our participation in the Innovation Festival from Northumbrian Water in July, right? Where we had a 4-day sprint purely focused on defining adoption strategies. So over 40 people thinking on what can we do with these models once they are released, right? How can we embed it into the organizational processes through different processes or different products, right? Looking not only at how a user can adopt them, but also what are the business value that it brings, what are the technical requirements that are needed for it. And similarly, we're working also with our consortium partners to bring in data scientists or business elements and start preparing people or bringing them into our teams, teach them about the models so they become then those early adopters, right? So they are starting to test, to run some experiments in parallel to our program, so that knowledge can be passed on. And ultimately, there is a very, very important track of this program, which is the TAG Academy, right? And this is a work stream that we set at the beginning or at the planning of the project, but we wanted to train young professionals to become these early adopters of our models, right? We want to empower this new generation to adopt this type of new tools and bring the change in the industry. So at the moment we have 7 candidates from different organizations in our consortia, and we're training them to become experts of these models. With activities, well, we had in-depth sessions for them to know about the project. We have provided the documentation, in-depth documentation as well, so they get acquainted with all the content of models. We have had different workshops, participation with the theme leads that you just met here today, but also with data scientists that were doing the work, and also going in depth into the different use cases that they can approach with these models. Ultimately, what we will, or they will work on, is on generating adoption strategies for their own organizations, looking not only on how to use the models, but what needs to change internally, what needs to be adapted in terms of processes and technology to bring these models into their work and become business as usual. So in a way, we hope we leave a group of people that is empowered and well, knowledgeable to continue to work with this. And of course, we invite you all to try all these models on GitHub, get back to us with questions, with suggestions, but of course, just adopt them. Thank you. With that, I'll pass it back to Leah for the final round.
Great, thank you, Gustavo. So I hope that's been a really useful and insightful presentation for our audience so far. We are just going to go into a final Q&A session for the last 15 minutes. And again, this is for any general questions you have for any of the project team, not just technical questions. My colleague is about to put another link in the chat to the technical exchange sign-up form for anybody who is interested in having that chance to explore the more technical side of the models in further detail. So make sure you do sign up to that if you're interested. And do keep popping your questions in the chat throughout the next sort of 10 minutes or so. Great. So to get us started, if all of our presenters could pop on their cameras and mics, please. Great. And going back to the questions from the technical portion that we didn't get time to answer, we have a question from Tom, who has asked, could these models reduce the burden of Section 82?
Do you want me to come in on that one? So it's something that we'll be exploring in the in use case 1 of how the models could be used to help make continuous water quality monitoring more efficient and improve the deployment of sensors to maximize the effectiveness of that monitoring and being guided by the output of the models.
Great, thank you.
So happy to say a couple of things on that, Leah. Yep. So within Northumbrian Water, it's a particular model of interest, but at the moment where we're looking at that in terms of reducing burden, obviously it's not at this point in terms of where we are with the water planning cycle. It's not going to reduce burden in terms of necessarily numbers, although I think it can contribute towards work around clustering for the deployment of monitors. But certainly, I think some of that burden reduction is potentially just in the kind of person hours saved in terms of automated processing of data as opposed to the kind of manual handling of it. And that's certainly where we see the model being able to go from where it is now, looking at anomaly detection through to then clustering, ultimately labeling as well. And I think there's some work at Nicola, you might want to come in on this. I know where you've been exploring, thinking of where you could take it beyond that and creating that kind of, I guess, library of anomalies and labeling. Obviously, the model itself is still dependent upon expert labeling to be able to validate the anomaly detection that the model will undertake. But I think in doing that, there's an opportunity to create a kind of encyclopedia or library of events there through future work. It's not where we'll get to by December, but it's where we see opportunities going forward. I think longer term, as Giles has said, I think there's an opportunity to inform beyond AMP9 as to, well, what could aid our catchment understanding going beyond the current deployment of Section 82 and challenging how that might be done differently. And I guess one of the things that's put to us is actually, could the work support less monitors more intelligently placed? So we're not advocating for more monitors in the environment, but actually less, but more intelligently placed. So not just asset focused, more to aid catchment understanding.
Great, thank you, George. Nicola, did you want to add any thoughts to that at all?
Yeah, I can add a few thoughts on what we've been thinking moving forward with that particular model. Is that we've seen trying to generate validation data sets and so on, and labeling Section 82 data, is that different experts have different ways of labeling the data, and there's some kind of inconsistencies between how they are labeled. So we definitely see a need or a benefit of getting people together, getting experts together to define a library or how to label continuous monitoring data and how to label events in continuous monitoring data to really benefit the most from getting all this new data.
Great, thank you. And question from Tim, do you think that the models that have been generated are better or easier to utilize than what is already out there at present? That's open to anyone.
I'll come on this one. So we're currently in the process of undertaking some benchmarking activities. So for each of the models, what we've done is identify existing tools or models or whatever that's already out there in the industry, and then these reports will try and compare how easy the models are to use in comparison to those, as well as some kind of cost comparisons and cost savings, if possible. And we're looking at things like what data inputs are required, what data science expertise might be needed to run the model, etc. So keep an eye out for that report or those reports soon.
Great, thanks, Dan. And Michael has said, thank you for sharing the models. May I ask if these can be replicated for Wales and Scotland? So far, obviously, there's been a focus on England.
That is model specific. So for theme 2, just because those are the ones on the top of my head, all of them, aside from the risk mapping, can be applied to the whole of the UK. I think risk mapping is limited to England purely because of the data inputs and the automation process for that. But there is not anything stopping someone kind of taking that code and editing where that data comes from, if you wanted to do so. So it's not that it couldn't be done, it's just we've run out of time, I suppose, in this project. Nikolai, do you want to do theme 1?
I just wanted to come in on that as well. And I think that underlines the whole reason for why we've released these models open source as well, is we wanted to show that it's possible to do it on a national scale for some of these models, and really enabling anyone who wants to do this in Wales or Scotland or Ireland and so forth to replicate what we've done. For theme 1, the flow model and the orthophosphate model is based on data from across England, but the E. coli model actually builds on Wales, England, and Scotland, at least for the light version. That should be already relevant for those areas. Yeah.
Right. And Chris, did you have anything you wanted to add for any of the models you took us through today? Or do we have Chris?
If Chris isn't there, the theme 3 model, as far as I'm aware, can essentially be applied using whatever data you put into it. So as long as you've got a CSV with your 5 or 6 parameters in of your water quality data, the model will run. So that's kind of can be applied anywhere.
Yeah, I think theme 3 is agnostic of any kind of jurisdictional or administrative boundary. And I think the point that was made is that we've tried to, as well as the model, we've tried to write the documentation up in a manner in which it provides a framework for application elsewhere. I think previous question, just to touch on, do we think the models we've generated are better or easier? I think that's too blunt to say something's better or easier. I think obviously we're looking at usability. Some of the models we created where there weren't comparable things that existed for some of the risk maps, for some of the reasons for not achieving good, and the activities there, we've created them to where there wasn't that. Others, I think they can be used alongside. What we're not advocating for is that, well, actually, our model is better than someone else's model. I think they have different values, they have different scenarios under which they might provide advantages or disadvantages over what you currently use. But the point is that the scale of the challenge is such that it's not going to be met by just one model. It's going to be, as Chris mentioned earlier, a hybrid approach. And there's a phrase I always come back to, which Dave Johnson in the Rivers Trust said recently at a Casco event, which is that all models are wrong and some are useful. So, we hope that they will be useful, but we hope that the learning and the transparency about how we've put the models together will be useful. I think that's a point of difference, is that we're trying to avoid a sort of black box scenario whereby you have to upfront pay a fee in order to then look at the models we've created. Central tenet of this project, and what makes it different, is that it is openly, freely available. It's being published open source via GitHub. So to a certain extent, I'll let others make their mind up as to whether they're more useful or not. But the good thing is you haven't had to pay for them, and there's an opportunity to be able to bring them in-house and develop them within your own, to meet your own sort of circumstantial needs, and with your own local data sets that you might have, where they can have more of a local applicability.
Great, thank you, George. And talking of the kind of collaborative use of these models, you've mentioned obviously that they're set up and shared so that they can be developed by other people. Harry has asked if there's a way of sharing how other people are actually using or building on the models, and to keep up with how the flows are being developed.
It's a great question. I think the main reason, or not the main reason, but we're open sourcing these models to allow them to live on beyond the funding of this project. That's been our focus all along, that this shouldn't stop when the funding stops for this project. And on the GitHub that we've shared today, the final iterations of our models will stay there. I don't think there's any plan to continuously update them on that GitHub, but it's open for anyone to clone and fork these models and continue developing them, continue to share them. We haven't set up any forum to do so or to share these things, but it's open for anyone to do so and continue this work beyond the project.
Great, thank you. And in terms of the scaling up of RDMAI, what is the ambition? So is the goal to apply this across all of UK river catchments or even internationally? And what do you kind of foresee as being the main blockers to scaling this up at a large scale?
So happy to take a first stab at that. In terms of scaling, I know certainly within Northumbrian Water, we're looking at the outputs from River Deep Mountain AI, and I guess the application of the project itself, if you like, is sponsored amongst the executive leadership team, as well as the project itself. So we have an intention to use the learning. We are at the moment sharing the learning to inform what Northumbrian Water's AI roadmap could look like. And again, that's not a roadmap that is built just on model output. It's built on the approach to this, the learning from it, and the kind of methodologies employed, as opposed to just the models themselves. Life is about timing and momentum. There's a lot of momentum built and learning amongst this consortia. Timing wise, we are hoping we can take some of this forward through follow-up Ofwat bids, which we're scoping and looking at the moment, as well as within the consortia and within some existing and water companies outside of that, as well as other partners, NGOs within it, where we think there are applications with hopefully enough business value to be taken forward outside of specific industry funding. So that's kind of what we're looking at the moment. In terms of longer term, I guess part of that measure of success is, I hope that the project informs other spin-offs outside of our control. I'm not trying to, we aren't trying to retain ownership as just staying within this consortia. That would be a grave mistake to try and keep it in that. So, for example, speaking to colleagues in other water companies who have referenced the coding that has been used to inform some of the bids that are being developed at the moment, which is absolutely brilliant. We've hoped that actually there can be quite a lot of use of this within academia as well, not just to support applied academia, where there are organizations already working with academics, and this coding, the output, will help inform that research and inform that going forward. So I think there's only so much we can track at our end. Metrics like looking just at interaction with GitHub are pretty coarse. But I guess amongst the consortia, we've got 13 organizations, such a large number. We're looking to try and continue working together, but hope that, I guess our hope would be we see the work we've done referenced and being used and bettered by others, taken forward and improved on. It's 15, 16 months we've had to work on it, which isn't a huge amount of time. So I think going forward, we'd love to see the outputs being used and kind of integrated into businesses elsewhere.
Great, thank you, George. And we've just had a final question from Mandy about whether you provide any training either in these specific models or on how to apply ML and AI to similar but different problems. I believe that's almost the purpose of the technical exchange, am I right? So I'll pop that link in the chat again for you, Mandy. If you want to sign up to one of those technical exchanges, they will be all about how to get the most out of the models and on the more technical side of things.
Just quickly on that, just around that final question. So we've got the technical exchanges. Obviously, we've got the Tag Academy we've been working on. I know one of the things we've been challenged, or I've been challenged by a steering group, is how could we, is the interest, and how could we continue to maintain a form of sort of community of practice from those people we've engaged with. I don't have the answer to that, but I would welcome thoughts, from participants on this call. A, as to whether there's appetite, and B, as to how that could be undertaken. It might be that actually things like the catchment data user group, that I believe the Rivers Trust Environment Agency kind of co-chaired, could be an avenue. SIOM, other industry bodies out there. We don't have to create something new, but we're very keen to explore how we might support a community of practice going forward. So welcome any suggestions on that.
I can add one more thing to that we are not just publishing the code on GitHub, but we are also publishing very comprehensive reports for each model. So those are also a great way to start on your own to learn about how the team has done what they have done.
Great, thank you, Miriam. And of course, there's also a written case study on the Spring platform, which will have links to these resources in it, alongside the recording from today for anybody else who wants to go back and watch this. I think that brings us to the end of today's session. So just to say thank you again so much to all of our presenters for the really hard work they put into the presentation today. And thank you again to the audience for taking the time out of your day to join us. We hope you found it valuable. Just a reminder to please fill in the feedback poll. If you have found it valuable, let us know what we've done well and what we could do even better to make adoption easier for you with this solution. We'll be sharing the slides from today's presentation as well, alongside the case study and the recording. So we'll let you know on LinkedIn when that's available if you give Spring a follow up on LinkedIn. Great. Well, that's the end. So thank you so much again, everybody, and I hope you enjoy the rest of your day. Thanks.
Thank you.
Thank you, Lee. Thanks all. Bye.